So good afternoon, ladies and gentlemen. Welcome to the first of two early career researcher takeovers of the UKCCSRC Autumn Web Series. My name is Patrick Brundle and I'm your chair for today's session. We've got three fantastic sessions lined up covering CO2 capture with adsorbents, so solids, subsurface flow dynamics, and hydrogen production. Each presenter will have 10 minutes to present their work, followed directly by 10 minutes of Q&A. If you do not have a working microphone, please feel free to ask questions during the presentation in the chat. I will ask them to the presenters after they've finished. And without much further ado, the first presenter is Phebe Bonilla, who is an environmental engineer currently studying a PhD at the University of Sheffield. Her project focuses on adsorption technology as an alternative for carbon capture. She's working on molecular simulations of CO2 capture utilizing hydrodacides as the adsorbent material. And without much further ado, Phoebe, the floor is yours.
Hello, everyone. Thank you very much for coming. I wasn't able to make my camera work, but hopefully it will be enough with the slides. So please let me know if you can see the slides.
Yes, we can see your slides.
Great, perfect. Okay, so let's start. Well, I've already been introduced. My name is Phebe, and what I wanted to talk about in this presentation is not exactly my project, but more a little bit about the context in which it fits in. So I'm going to talk about the current pilot scale projects using adsorption as the possible alternative to the commercial chemical absorption. So as we already know, we have this goal of getting to net zero into the middle of the century. And the main problem remains that we need a technology, or we need any kind of strategies that will allow us to reach that. So CCUS, it's of course our chosen technology for the moment. However, it's been estimated that we need around 2,000 facilities, large-scale facilities, to deliver this net zero goal. And this has to happen by 2040, which is not that far away. And if we can see the results from the core, or the database from the International Global Institute for CCS, we just have around 187. So if you can see, we're actually a little bit behind, but well, I'm hopeful this will change in the following years. So another thing that I wanted to point out from this database is that not all the projects that have been reported are currently operational. So the ones that are open and functioning are about 74. 53 have been just a demonstration project which has terminated, and well, we cannot count on them anymore. So as you can see, there's few in planning, construction, development. However, well, we still need a lot more, especially at this scale. And what I mean by large scale is, at least in this database, is around 800,000 CO2 tons per year. If you are talking about a power plant based on coal fired coal, sorry, well, burning coal. So there's other databases and there are other projects also working on adsorption. However, they are in smaller scale, or sometimes they are not actually publishing all the efforts they are carrying out. So what I have found in this database is that most of the projects currently are in the USA, regardless of how the Trump administration regarded climate change. I also found interesting that China has a lot of the big large-scale facilities development, because most of the events and most of the articles I've read are from facilities that are in Europe and Northern Europe. So, well, as you can see, the facilities are spread around the world, and most of the ones that are concentrated are because they are next to a storage facility that enables these capture projects to go directly into the storage. So usually they are near enhanced oil recovery projects. However, well, there's others that have this partnership between industry facilities such as cement or steel factories. So what are the challenges of actually implementing all the CCS we want? As you should know, carbon capture is mainly the most expensive part of all the CCUS steps. And this is because it requires a lot of the energy. You can actually use 1/4 of the energy you produce in a power plant only to capture the CO2, which is not very convenient. And that's why we haven't been able to implement it all around the world so easily. So from the technologies available, I'm going to focus on post-combustion because adsorption, this alternative I'm looking at, is best fit for post-combustion. And also because post-combustion can be easy to retrofit in power plants and also industrial applications, as I mentioned. And it has a benchmark already since solvent absorption has already large-scale facilities. So another advantage of post-combustion is that it is easy to transfer. So there's many temperatures and pressures at which it can function. So the 4 main ways we can do post-combustion capture are using membranes or liquid absorption, which is the mainly mature one, solid adsorption, which is the one I want to look at, and cryogenic distillation. From this, adsorption promises to be a good alternative. And well, what is adsorption? It's an exothermic and spontaneous process. So what we can see here is a very basic representation of it. So we have the adsorbent material, which is a solid, which has a lot of porous, intricate the surface. Usually, if you have more pores, then you will have a bigger surface area, and that would allow you to capture even more CO2. However, this is not always the case because the interaction between the CO2 and the material also depends on the nature of the material. So if you have some anions or if you have other metals that attract CO2, you can enhance the adsorption capacity without increasing the surface area. So what are the advantages of adsorption? First, it usually requires lower energy penalty for regenerating the adsorbent, which is one of the main problems with the current commercial absorption. Next, we have a lower capital and operational costs, which are derived from this lower regeneration cost, and also because depending on which material you use and also the configuration of your reactor, you can reduce the footprint of your capture unit, and that also reduces the cost. Again, it has a wide operability range, so you can do adsorption from very low pressures to high pressures, depending on which material you're using. And also from temperatures, again, depending on your adsorbent, you can go from 40 degrees, which is kind of the normal comparison for the adsorption materials, until 500, which is high temperature capture, which is more applicable to industry settings rather than power plant facilities. But well, as you can see, you can have a wide application of it. And another thing that looks promising is that in contrast with absorption, when you have finished with the process and your adsorbent is spent, then you don't need a specialized waste treatment. So in the case of absorption, you usually end up with amines that can be bad to release to the environment because they are corrosive and they can have other effects that you don't want. So these advantages look very promising. However, to implement it at the big scale that we are talking about in the beginning, there's still a lot of challenges that we have to overcome. And interestingly, these challenges have been around since we first thought about using adsorption for carbon capture. So the first one, we have that the selectivity of the adsorbent material for the CO2 in contrast with the solvents is lower. So depending on your material, you might need more material or more adsorbent, more volume of adsorbent in contrast with the solvents. So if you increase the selectivity, you might increase the adsorption capacity and thus reduce the amount of material you need and space. The second thing is for the adsorption capacity, depending on the size of the pores of your material. You can also try to get as much CO2 into the small corners of the pores. And this is not as high as the chemical absorbent. So there is a trade-off between how much you can capture at these different pressures and temperatures that you cannot achieve with solvents, but it's in a lower capacity. So you have to look at which is more convenient for your setting. Next, we have scalability, because the production of the adsorbent hasn't been completely commercialized. And as we will see later in the projects from the database, there's many different materials, there's many synthesis methodologies for each one of them, and not all have been completely refined. So scalability of the production of the material still is a problem. And furthermore, for the adsorption, as it is an exothermic reaction, then we have the problem that the more material you have, then you have to get some measures for improving the temperature gradient between inside your reactor. And well, it is a new technology in contrast with absorption, which has been around since 1930s. Absorption for carbon capture was implemented until 80s. So, well, we have a lack of expertise. And that's when the question arrived, like, well, okay, if it's so promising, where are we at in this moment? So for the methodology of this presentation, I made a survey for the adsorption projects large scale for post-combustion into databases, the core, which is from the Global CCS Institute, and from the National Energy Technology Laboratory, or NETL, from the Department of Energy of the United States. And I assigned a technology readiness level, which is basically just a number to give us a very superficial way to look at the project and to see how far we've got with adsorption for carbon capture. So according to the Nuclear Decommissioning Authority, the way to assign the technology readiness level is depending on how advanced your project is and the conception of the basic principles, like you imagining it is the first step. Second is actually putting into work and see how it can be done. 3 is that you have already proved that it works. 4, you start bench scale research. 5, you get to pilot scale, and then you just grow from there until you achieve a working facility. So from the databases I revised, the projects of adsorption for carbon capture were just achieving on the pilot scale. So what I found was that adsorption is actually a very small piece of the puzzle in carbon capture yet. So from the databases, they are a very, very small fraction of all the projects available. And most of them are just in the bench scale. So I'm not going to read out loud all the tables. What I want you to look at is kind of the amount of text you can find, because the way that the information is spread out is very weird. There's projects that can explain you everything, very detailed, and some that don't have enough information. So For the core database, I found only 4 projects working on adsorption, and most of them were in the bench or pilot scale. And for the nettle, it was 7 projects, and most of them were at bench scale, although they provided much more technical details. So in summary, what we found was that the adsorbent which is most popular right now are the MOFs, or metallic organic frameworks, because they're usually easy to tune. However, they are very expensive to produce. So they're usually the ones that cost more, and the process is not commercialized yet. So most of the other adsorbents in the projects were bought, and the MOFs usually were developed by the project itself. So that's why it's kind of hard to decide how far we've got with it, because MOFs are really good, but they're very expensive. And on the other hand, we have that the regeneration process for the adsorbent, it's mostly by temperature swing adsorption, which is by just increasing or decreasing temperature. However, a pressure swing adsorption, which is very similar to vacuum swing adsorption, were also present. But this does not indicate the general status of the adsorption as a technology for carbon capture, because it has many details that you have to look at. So, for example, we have the reactor type, which usually for fixed beds is it's cheaper than a fluidized bed. And also, there were projects which were comparing exactly these 2 types of configurations, and they hadn't decided yet on which one was best, because it also depended on how you obtain the energy to regenerate your adsorbent. So, for example, if you had a temperature swing in a fixed bed, it could cost $4 per ton. If you got the energy from the process and you were kind of recycling the energy. Whereas if you used an electric swing adsorption, then it doubled in cost. So in conclusion, absorption is the most mature technology yet, but adsorption is still a viable alternative. However, the knowledge is not shared, like all the projects kept to themselves, and it didn't feel as if the projects were taking advantage of being in the database. They were just reporting, but not actually sharing what they had learned. Adsorption for carbon capture is between invention and research and pilot scale yet. So in contrast with absorption, which is already active in level 9, adsorption still has a lot of way to go. And the main challenges to achieve this are the affordable production of the adsorbent, which should be cheap, the heat management because of the exothermic reactions during the capture, solid handlings because most of the adsorbents are can be attrition, like the pellets could generate dust and that could generate problems in the fixed bed. And finally, some of the adsorbents are really sensitive towards pollutants in the flue gases. So I leave it there, and I hope there's time for questions because I think I just overdid my time a bit. Thank you very much for listening, and yeah.
Thank you very much, Phoebe. Much appreciated. We've got time for 2 or 3 quick questions. So you can either use the chat or unmute. And I'm quickly going to ask you one question straightforward. So you mentioned the different process layouts, fixed bed, fluidized bed, rotating pack bed, or ear, as well as pressure swing adsorption, temperature swing adsorption. Is there a general consensus what the best configuration is, or does that matter what adsorbent you're using?
So in the projects I observed that fixed bed was kind of the easy way to go because there's so much work done on fixed bed already. So it was easier to go with that and just adjust parameters rather than to create a completely new configuration. However, there were projects that really tried to change things around, and they achieved a much higher adsorption capacity. by changing both the way you put the adsorbent and the type of reactor. So the results look very promising, but their stage is still at level 2. So they haven't figured out yet how to scale up those results. So you could say that conventionally speaking, it is most common to see fixed beds, but it's seen that fluidized beds work best, but we haven't got it right just yet.
Thank you, Phoebe. We've got a question in the chat from Ian. Ian, do you want to ask a question yourself, or should I forward it to Phoebe?
Okay, yes, so well, I'll read it out basically. Presumably carbon capture in coal is an absorption process. Would you have any comments to make relating adsorption in coal to any of the work you're talking about today?
You mean adsorption in coal or adsorption in?
Yes, coal, yes.
So, well, I usually look at adsorption after the combustion of the coal. So what I've seen is that you have activated carbon as an alternative adsorbent. So I haven't looked at any projects having coal for adsorption, but in activated carbon, it actually works better at high pressures and low temperatures for carbon capture. I don't know if that answers your question.
Great, thank you. Thank you, Phoebe. And with that, we're moving on to our second presenter. Catherine Spurin is a PhD researcher in the Department of Earth Science and Engineering at Imperial College London, and she's funded by the President's PhD Scholarship. Her research focuses on dynamics of subsurface flow using laboratory-based micro-CT and fast synchrotron imaging. And with that, Catherine, the floor is yours.
Can you hear me and see my slides?
Yes, we can.
Great. So the work I want to present today is some recent experimental research where we captured in unprecedented detail the flow dynamics in rocks as the flow in the porous medium transitioned from transient to steady state. And I do this with the supervision of my two supervisors, Martin Blunt and Samuel Clever. So the reason that we were interested in this is that it's very important for the modeling of subsurface flow, including CO2 storage underground. So transient dynamics are assumed to occur relatively rapidly compared to the macroscopic properties, such as the pressure in the reservoir or the saturation, which means transient flows, such as the injection of CO2 into a reservoir, are modeled with steady state properties. And this is shown in the diagram on the left here. But the underlying assumptions to this is that the pore scale processes are the same for steady state and the transient stage, so the unsteady state, and that the fluids flow in connected pathways at steady state. So the first question is like, are these assumptions valid and can we model the flow like this? So the first thing is, do fluids flow in these connected pathways at steady state? So when we're wanting to model subsurface CO2 flow for CO2 storage, what we do is we use reservoir models to predict the flow and trapping in the subsurface. And this has a number of key inputs into the reservoir models, such as the capillary pressure and the relative permeability. And I won't go into these in more detail, but what I'm saying is that these parameters hinge on the fact that these fluids flow in continuously connected pathways. But what we've already observed in our experimental data is that fluid flow isn't that simple. So what the graph on the left shows is the capillary number on the y-axis and the mobility ratio, which is the ratio of the fluid viscosities on the x-axis. And on this figure, I've just indicated some typical capillary number and mobility ratios for subsurface flows. So you can see in box 1 here, this is the region where CO2 storage and natural gas production lie. And what we see is that we expect these intermittent flow pathways to occur in the subsurface at these scenarios. So an intermittent flow pathway occurs when the gas is continuously connecting and disconnecting. And this has been described in the past as cars being stopped by traffic lights. So the flow networks remain relatively the same, but the flow networks aren't always continuous, and the gas can be trapped and then reconnect and then disconnect again. However, all the research that we've done so far has been in time averaged imaging in the micro CT labs we have at Imperial. And what this means is that the intermittency has never been fully resolved. And what we've had before is like this image here on the right. And in this image here, the rock grains are transparent. These gray regions are the brine. This blue is the gas. And these green regions are where the phase change has occurred during the scan. So this is where the intermittency is occurring. And you can see it's occurring, just say, in this key region here. But we weren't able to capture the dynamics directly. And so we weren't able to capture the transition from transient to steady state. However, we have been able to do these experiments in a synchrotron in Switzerland. And we now have 1 second time resolution, which means we are able to capture the dynamics. So this is just a video of one of our experiments. And so in this video, the gas is shown in red and the brine is shown in gray. And what we did is for this rock, we saturated it with brine, and then we simultaneously injected both brine and gas, and the flow is in this direction that I've indicated with the arrow. And what you can see is that the gas propagates in these large bursts, which we already knew were called Haynes jumps. And we were able to compare these dynamics that we saw during this transient stage with the dynamics that we observed at steady state. So this is just a graph of all the experimental parameters. So on the figure on the left, we have the gas saturation on the y-axis in red, so all these red X's. And then we have the pressure drop across the core, which is an indication of when steady state is achieved, because the pressure drop will plateau at steady state. And that's shown by the black line. And on the x-axis, we have the time after injection. So what this graph shows is that initially the gas is percolating the sample, and we have a rapid increase in the gas saturation. Then it percolates across the sample, and we still get an increase in gas saturation, but it's much flatter at this point. And then at steady state, the gas saturation is basically constant, but it is fluctuating about a mean. And then what you can see in the pressure readings is that the pressure rate is increasing during unsteady state. And then at steady state, it is fluctuating again about a mean. And what I've shown on this left-hand side is some numbers. And on the right-hand side, this is the same, the pore space at the same time. So what you can see in figure 1, between 1 and 2, we've had these large bursts in the gas traveling across the sample. And then at steady state, the dynamics are much more subtle. And so I've just provided the zoom in. And what you can see here is an intermittent pathway. So it's connected, it disconnects, and then it reconnects in the same place. So like I just said, the steady state dynamics are much more subtle. And so playing this video now, it might look like not a lot's going on, but I just want you to focus on this region here, because it's the most obvious. So if I just speed this video up, you can see it connects at this point. And actually a lot is going on. It's just only a small amount at like a given location, so it's harder to spot. But as I showed before, these intermittent pathways can occur at very key locations, and such they have a huge impact on the connectivity of the fluids. So the graph on the right shows the number of distinct ganglia per unit volume. So that's the number of disconnected gas regions. And on the x-axis is the gas saturation again. And I've split this into 3 different colors. So blue is unsteady state dynamics before percolation, green is unsteady state dynamics after percolation, and the red is steady state. So what you can see is that when the gas is percolating the sample, it increases the gas saturation quite significantly, but not at the expense of how many disconnected gas blobs there are. However, once the gas has percolated the sample, we see that the gas saturation is increasing still, but also so is the number of ganglia. And this is it optimizing the pathway post-percolation. And then at steady state, what we see is a very narrow range of saturation. It is fluctuating around the mean, and it fluctuates around the mean by about plus or minus 15%. However, there is a huge impact on the number of ganglia and therefore the connectivity of the gas, shown in this direction. And in fact, the number of ganglia is fluctuating plus or minus 70% of the mean. So this just highlights that we have a huge impact of these intermittent pathways at steady state, and this is something we cannot ignore in the modeling of the subsurface. And just because the dynamics are so subtle, I have this zoom in of the pore space. So this is the exact same video as before, just I've zoomed in onto a couple of pores. And what you can see is that just as I shown before, it will disconnect here, and then it connects, and then it disconnects again. And so this is just a good example of the impact these intermittent pathways have, because without this connection, it might look like this gas ganglia is trapped, but that is not the case. And so when you are calculating the capillary trapping in the pore space, you have to remember that everything that might seem trapped in a static image is not the case, and the dynamics are actually much more complex. So I've shown you these videos, and we kind of qualitatively see the differences between the transient and the steady state dynamics, but we actually really wanted to quantify the differences between the two. And so what this graph here shows is the number of events observed within a 30-minute imaging window on the y-axis, and on the x-axis is the intermittent event size in the number of pores involved. And what you can see is I've split it again into 3 scenarios, but this time unsteady state 30 minutes after percolation in blue, unsteady state 1 hour after percolation in green, and then the steady state dynamics in red. And what you can see is that the unsteady state dynamics involve large bursts, which I referred to as Haynes jumps, and these can involve up to 35 pores. But the steady state dynamics on this end only really ever involve 1 or 2 pores, and at the most 3. So this is just the quantifying the fact that these steady state dynamics are very subtle, but they are having a huge impact on the flow. And so we wanted to be able to equate this to the impact this would have on subsurface flow for CO2 storage. And we do this by analyzing the plume mobility. So what I showed before is that after percolation occurs, the gas saturation increases slowed. But what you can see here is that actually the gas saturation plateaus out much sooner than the pressure does. So at this point here, oh, that was a bit messy. This point here, the saturation has already plateaued, but you can see that the pressure is still increasing at the same time. Whereas here it is plateaued, but the pressure is also plateaued. So the fact that we have the same saturation here, but a lower pressure means that the mobility is actually higher during the unsteady state. And so if I equate this to a graph, what it means is that actually this unsteady state part of the plume shown here on the right is more mobile than before, which means that the plume will travel further than you would expect if you use steady state properties. So the question is, how much of the plume should I model using unsteady state properties? And we just did a rough calculation for this, and we calculated that it took 180 pore volumes for steady state to be achieved in our rock sample, which would equate to 3.6 meters of the plume front being unsteady state. And you might think, okay, 3.6 meters or 4-ish meters isn't very much. But if you have a very complex geology with lots of, say, mud rock layers, which is the case in the Sleipner field in the North Sea, then actually this unsteady state plume front can have a huge impact on your dynamics and a huge impact on how you should model the CO2. So to conclude, these intermittent pathways that I've been studying for my PhD are very important for CO2 storage because they play a very important role in the fluid flow and the connectivity, and they may have a huge influence on the trapping if you stop flow. And using synchrotron imaging, we revealed that the transient part of the plume is more mobile than during steady state, and this has an impact on the dynamics that we would expect in the subsurface. So with that, I have a lot of people to thank. A large team came with me to the synchrotron and helped me perform these experiments, and I would like to thank them all. And for further information, this work is published online, and you could either email me or you can click these links, and you can check out all the videos again on my YouTube channel.
Thank you very much, Catherine. Nice to see your YouTube channel getting a plug here as well. If you want, leave us the link in the chat, please, and then people can directly click on it and check out those videos again. So please feel free to ask questions or raise your hand again. And I'm starting off with the first question. So you tell me that the differences are very subtle but have large impact. So if I want to model the difference, is there an easy way how I can implement those new findings, new results into existing models?
So at the moment, I'm trying to work out a way to put the results that we see into like a correction factor on the relative permeability. And what it seems is that the type of intermittency and the impact that the intermittency will have on the flow scales with the capillary number of the system. So this is kind of like an ongoing area of research, but what we find is that the pore geometry is really key when the capillary number is low. But when the capillary number is high, actually the pore geometry plays less of a role in the intermittency that we see. And I'm hoping that we can use this to basically put a correction factor into the relative permeability curves. But like I said, it's still a little bit ongoing.
All right. And if I have to predict, and under European law at the moment, you have to predict the movement of the plume. If I'm not including the new findings, by how much would I be inaccurate? Would I have to oversize my region that I think the plume will move, or will I be taking the risk and the plume moves outside my space?
So that's very geology dependent. Obviously, all the CO2 storage sites are vastly different, but it's like the example I gave was Sleipner, and the modeling efforts for there have historically always been notoriously bad. So the fact is that we have a pore scale mechanism that could explain why these models are so bad. There would need to be more research into exactly how these pore scale processes manifest in the really large scale flow, large scale processes where you have maybe large faults, varying lithology and things like that.
That's great. We've got time for one more question, if there is one. Last chance. And then thank you very much, Catherine, again. And then we move on to our last, but by no means least. We have Harry Yan, and he's a final year PhD student at Cranfield University, working on high temperature solid looping systems for carbon capture, thermochemical energy storage, and low carbon hydrogen production. His research is also focused on harnessing the power of machine learning techniques for energy process systems and material developments. And with that, Harry, the floor is yours.
Okay, thank you, Patrick. Good afternoon, everyone. Welcome to this webinar. Today, I will talk about techno-economic analysis of low-carbon hydrogen production by sorption enhanced steam methane reforming process. So as we know, hydrogen is a versatile feedstock that is widely used for oil refinery, ammonia production, and also other useful chemicals production. And the low carbon hydrogen is an attractive clean energy carrier, which can be used for the clean energy transition. So, but the current hydrogen production is mainly focused on the steam methane reforming, which produce lots of CO2 during the hydrogen production. That contributes about 2.6% of the global CO2 emission in 2019. So, in order to reduce the CO2 emission from the hydrogen production, in this work, we investigate a novel process, which is called sorption enhanced steam methane reforming, which is combined the SMR with the cathode looping. So we put the solvent inside the reformer. During the natural gas reforming, the produced CO2 will be captured by the solvent, and the whole reaction is shifted to the right-hand side in favor of more hydrogen production. But one drawback of this process is we need a proper heat integration to reduce the additional CO2 from the regeneration of the CO2 solvent as well as the steam production. So in this work, we investigate the techno-economic feasibility of the SE-SMR process integrated with aux-fuel combustion, chemical looping combustion, and the biomass-fired consumer. So we evaluate the process performance in terms of the net efficiency, CO2 capture efficiency, and the levelized cost of hydrogen, and also the cost of CO2 avoided and the removal. So we proposed 6 different cases, and we use the Aspen Plus software to do the process simulation and the heat integration. We follow a typical chemical plant cost estimation methodology to investigate the capital and operating cost, and also the economic performance of the proposed sorption enhanced steam methane reforming plants. So this is the case 1A and case 1B. So we got the SE-SMR process with use the air-fired consumer. So this is the case 2A and case 2B. So we use the aux-fuel process to provide the heat for the consumer and the steam generation. So in the case 3A and case 3B, we integrate the chemical looping process with the SE-SMR process. So this figure shows the key performance for the proposed SE-SMR process. So as you can see, the case A, which is the SE-SMR process integrated with air-fired consumer with the natural gas, so it can achieve the highest net efficiency and the lowest level cost of hydrogen. But only 60% of the CO2 can be captured during the hydrogen production. So with integrated of aux-fuel and the chemical looping combustion, we can achieve nearly 100% of the hydrogen CO2 captured. And among them, the case 3A, which is the SE-SMR integrated with the chemical looping, it can achieve the nearly 100% of CO2 capture with a higher net efficiency and the lower level cost of hydrogen. So this figure shows the level cost of hydrogen for the proposed cases and also the distribution of their components. So as you can see, the orange bar, which is the fuel cost, and the capital cost account of the large share of the level cost of hydrogen for the proposed cases. So we also calculate the split of capital cost and also the operating cost. So as you can see, when we integrate with aux-fuel and chemical looping, we will increase their capital cost by about 25% to 50%. And for the operating cost, we can see the electricity for the CO2 compression and also the CO2 capture, CO2 storage cost will account for the major cost of the operating cost. So we also do a sensitivity analysis to evaluate the 6 different K parameters on the impact of level cost of hydrogen. So as you can see, the fuel cost, the level cost of hydrogen is more sensitive to the fuel cost. So we also calculate the cumulative discounted cash flow with the assumption of the different hydrogen selling price. So in this figure, you can see when the hydrogen selling price is £3 per kilogram, all the investment of the proposed SE-SMR process can be paid back after 8 years. So to conclude, the level cost of the proposed SE-SMR plants ranged from 1.9 pound to 2.8 pound per kilogram, and the cost of CO2 avoided ranged from 33 pound to 69 pound, which is comparable to the SMR integrated with amine-based scrubbing system. So by applying a carbon price, so the cost of CO2 avoided and the removal for the proposed cases can be significantly reduced. So this work provided a flexible option for low carbon hydrogen production in terms of the costs and the demand of the CO2 reduction. So that's all. Thank you for your attention.
Thank you very much, Harry. That's a fantastic presentation. Again,
thank you, Patrick.
To ask questions either in the chat or on the mic, and I will open with the first question.
Yeah.
So this is blue hydrogen, and people talk about different colors, and maybe you can explain what the different colors of hydrogen mean. It looks like the European Union have this big hydrogen vision, and maybe you can comment on how absorption enhanced methane reforming fits into this vision.
Okay, so we currently got we got different color. It means different pathway for the hydrogen production. So the first one is the green hydrogen production, which is the traditional way for the hydrogen production, focused on the fossil fuel like natural gas reforming and also the coal biomass waste gasification. So in this process, the green hydrogen doesn't have the CO2 capture facility. So when you integrate the CCS system with the natural gas reforming or biomass gasification, coal gasification, you capture the CO2. So we change the color from green to blue. So this is the blue hydrogen. So another one is the green hydrogen. So as we know, we use the renewable energy such as solar, wind to produce the hydrogen. We don't have the CO2 emission, so we call it green hydrogen. So this is the three main different colors for the hydrogen production. I think it's another one is called white or something. Maybe I'm not sure. Maybe the negative CO2 emission. Maybe the biomass gasification is integrated with the CCS. So we during the hydrogen production, we actually remove the CO2 from the atmosphere. So it may be called the white hydrogen, but I'm not sure. I need to double check. But the main three pathway is green, gray, and blue. So yeah.
Great, thank you for that. You mentioned the process is really flexible, and I keep hearing that the future energy system needs to be very flexible. So is the new absorption enhanced steam methane reforming more flexible than conventional steam methane reforming?
Okay, so the flexible means like because in this slide you can see we got different different degree of the CO2 capture efficiency. So as I said, it depends on the cost and the reduction of CO2, the demand of the CO2 reduction. For example, if the guidance like if for the hydrogen plant, if you just need 60% is enough, and also you just have that much of budget, you probably go to the case A. So if you want the 100% of CO2 capture efficiency and you have that much investment, you can go to the case A. So it's based on the cost and the demand of CO2 capture reduction. So it's not focused on the operation capacity factor. So I didn't compare the operation capacity operation factor for the we got the high demand, low demand, how to change the operation load or something. So it's just a focus on the demand of CO2 reduction and also the cost of the investment.
Yeah, it's very interesting to see that you can reach near to 100% capture at an interesting increase of capture. Mm-hmm. And one important note there quickly, this assessment that you're showing here on slide 6, does that include the £16 carbon tax that you
no, for this one I didn't. So I got another figure in my paper. It has the cost of like £16 of per ton of CO2 carbon price. So that one it can further reduce the cost of the level cost of hydrogen. So it's around 1.8 to 2.3 or something like that. So this one is not include the carbon price.
That's interesting. That's great.
Yeah.
And just a comment, would you think that blue hydrogen will be dominating, or is it that green hydrogen will be dominating? How important will be blue hydrogen?
Yeah, so it's like the role of the CCS with renewable energy. Do we need like do we need CCS, or we just use the renewable? So it's the same. Like for the if you look into the cost for the current technology for the green hydrogen, the level cost of green hydrogen is around, I think it's roughly around £5, something like that. It can be further reduced after 2030 or even later years. But you should think about we in this paper we cite large scale block continuous hydrogen production. So we know the renewable energy have the nature of intermittency. So I mean, it's from my point of view, in the future probably mixed. So we probably have the like the baseline. We can use some of the blue hydrogen technology to provide the part of the hydrogen demand, and we can also combine with some green hydrogen. So we can to meet the demand of the hydrogen, the increasing demand of hydrogen in the future. So I think it's a mix. So mix blue hydrogen with the green hydrogen. But currently, the cost of green hydrogen is high. So we need to do more research to reduce that kind of cost for green hydrogen.
That's interesting. That's literally the question that Philip Sharman just asked in the chat. How does the cost compare to green hydrogen, essentially? And comment on that again. I think the European Union is betting on green hydrogen. The UK is moving more towards blue hydrogen. So do you think the cost of blue hydrogen will come down as much as green hydrogen? Because at the moment, as you just pointed out, green hydrogen is much more expensive than blue.
Yeah, but I didn't do too much research on that. But from my present review, I think, yeah, the UK have invested lots of money on the different project for the blue hydrogen production. So I think the cost will reduce, but yeah, I'm not sure it will be like the development at the green hydrogen. But we need more attention, we need more investment, we need more research, so we can do more reduction in the cost for the blue hydrogen.
We always need more funding for research. I agree with that. And I see in the chat, Robert mentioned 50 kilowatts hour per kilogram of hydrogen, the energy demand. And something interestingly is, if you compare the different pathways of hydrogen, the demand of hydrogen, there are lots of moving pieces. So I think we will not be able to answer in one webinar the future of hydrogen here. And I think there's a big disagreement between the UK and the European Union in terms of the direction and the competitiveness of those technologies. So Harry, thank you very much.
Thank you, Patrick. Thank you, everyone. Yeah, I'm stop sharing.
So thank you all for joining the Early Career Researcher takeover of the first takeover. Next week will be the second takeover, so please come back. Make sure you check out the posters on the webpage, check out the YouTube channel from Catherine, and also on Twitter, you can answer or ask Harry some questions. Phoebe's on Twitter as well, and I'm pretty sure they're happy to answer all of the questions.
Sure.
Thank you,
Patrick.
Yeah, thank you. So just to say from us at the UKCCSRC, thank you very much, everybody. Patrick, Phoebe, Catherine, and Harry for today, for the as Patrick says, the ECR takeover. And again, as Patrick says, we've got another one next week, and the posters for that are on the website. I could quickly just let you know it's Louise Handy from Swansea University, Mikhail Gorbanov from Brunel University,
and Grazia Leonzio from Imperial College London. And the titles and abstracts of their posters and their presentations are all on the website, as Patrick says. So thank you to everyone, and hopefully see some of you again next week. Bye for now.
Thank you, Patrick. Thank you, everyone.
Thank you.